Next, we are going to focus on direct proof. So direct proof here simply means that you are actually using mathematical direct proof in order to prove a statement, whether it's um, true or false, or whether it's a mathematical or algebraic calculation which requires proof. So for example, prove the following universal statement. Yeah, for all integers n, 4 multiplied by n squared plus n plus 1 minus 3n squared is a perfect square. All right, so the proof is stated. So when you need to prove such mathematical algebraic related proof, of course you must show some algebraic working, right? So for example, let n be any particular number, or let n be in any integer. Okay, so we don't use decimals. Most of the time we use integers, yeah? And you're supposed to show that the 4n squared plus n plus 1 minus 3n squared is actually a perfect square. So you have to find a way to factorize it and show it's a perfect square for all values of n. So what we're going to do here, we're going to try to factorize 4n square, 4 multiplied by n squared plus n plus 1 minus 3n square. So we expand it, rearrange it, and we try to factorize it. So now for n plus 2 square, um, obviously this is a perfect square, right? So we have kind of like have proved the statement, but you need to write out a concluding statement usually. So what you need to do is n plus 2 will be a perfect square for any integer of n. Okay, so therefore this proof is complete, right? So you can think, if n is an integer 1, 2, 3, -1, and whatever, so on, any whole number, right? So when you substitute any number as n into here, and when you square it, it's definitely going to be a perfect square because it's squared, right? So therefore, this completes this particular proof. Okay, so these are called direct proofs. So direct proofs can come in varying ways. It can be algebraic, sometimes it's logical. Yeah, so you need to think, but you need to write your proof in terms of mathematical statements or calculations. Yeah. So now we will look at some more indirect proofs, which we're going to learn about proof by contradiction and contrapositive, but we'll focus more on contradiction here, yeah. So now we will visit the one of the method of indirect proof, which is proof by contradiction. Sometimes some mathematical statements can be quite tricky to actually using direct proof. So we need to use the indirect proofs like contradiction. So before this, we have done direct proofs, okay, like the Pythagoras theorem just now and so on. So in order to prove an implication, if P then Q is sometimes difficult or impossible to directly prove. So we need to use contradiction method. Okay, in this case, contradiction is, or you can use contrapositive, yeah. So the contrapositive negation here simply means if P then Q, or if Q then P. All right. So the not Q and then if not P is true, so P is, if P then Q. So this simply it might not mean so much to you now, but I will try to use an example in the next slide to actually explain to you. So for example, if you have proof a plus b over 2 is more than and equal to third of ab for all values of a, and b is actually element of a natural number, yeah. Okay, so for example, assume you have to make an assumption, right? You have to make an assumption. So your assumption will be always the opposite of what the proof requires. It's called a contradiction for a reason. So you start off by contradicting the original statement. So when you want to contradict larger than and equal to, the contradiction of it will be less than. That's why this method is called contradiction. Okay, and so over here is just algebraic. So once you get the contradiction, now what you're going to do, you do a contradiction and then you prove the contradiction is actually false. Therefore, your original will be true. So that's why it's called method by contradiction. All right. So first step, you contradict your original statement. All right, and then you try to prove that it's actually wrong. So in this case, what I did was I brought the 2 up, and then to get rid of the cert, I have to actually square both sides. So when I square both sides, I actually get this, or I expand it, I got this, okay, and I tried to bring it over for AB over and try to factorize it. When I tried to factorize it, I actually got A minus B squared is less than 0. So this simply shows that A minus B less than 0 is obviously false, right? Because if A and B, is any value and B is an element of natural numbers, then obviously A minus B squared cannot be less than 0. It has to have a value which is it has to be positive value, because A minus B square is definitely, for any value of A and B, is obviously a positive value. It should be higher than 0. So therefore this statement is actually false. So therefore, since the contradicting statement for the original question is actually false, so the assumption is actually false, right? The contradicting assumption is actually false. So therefore, or hence, your original statement. Okay, so for the next example, we're going to look at proof that the set of primes is infinite. So prime numbers are basically the numbers that you can actually divide by itself and also number 1. Yeah, so those are prime numbers, and you have to prove that the set of them are actually infinite, okay, or infinite. All right, so you can't prove this directly, all right. So you have to use some mathematical proof. So in this case, I actually wrote as, suppose the set of primes is finite having n numbers. So example, it will be P1, P2, P3 up to Pn. We don't know what n is, right? So hence a number exists that it's the product of all the primes, okay? So example, I'm assuming that the set of primes are actually a product of prime. So I'm taking that as n. So a product of prime numbers will be obviously P1 times P2. It's a product, so it's a multiple, yeah? P1, P2 times Pn. And next, now you have to consider the number after n. So the number after n is obviously n plus 1. Means like the 5th term, and then the 6th term will be 5 plus 1. That's what it means, okay? So n plus 1 is obviously the product of n plus 1 prime numbers will be P1, P2, P3, and so on. And obviously it will be Pn, and always there'll be a plus 1 at the end because it's n plus 1. So if we attempt to divide n plus 5 as n plus 1 with any of the known primes between P1 and Pn, when you divide, obviously because it's n plus 1 divided by any other prime number, so obviously you will have a remainder of 1 always, okay? So therefore, n plus 1 you cannot divide, it's not divisible by any prime number greater than 1 apart from n plus 1 itself, because n plus 1 divided by n plus 1 you will get 1, okay? So therefore, so prime number is greater than the largest prime number Pn. So therefore, the supposition